Hello and welcome to a digital lecture for Solid Community College. This lecture will cover section 6.5 for Intro to Statistics, considering inference for linear regression. When we are going to perform inference on least squares regression lines, we generally require the following four conditions. These are the conditions that we're going to want if we want to use hypothesis testing. The first condition is linearity. This means that we want to make sure the data shows a linear trend. We can usually confirm this either by looking directly at the regression plot itself or by looking at the residual plot. Secondly, we want to have independent observations. We really want to make sure that we are cautious about using any data that could be associated with a time series. When we have a time series, data that is collected over a period of time, that usually means that we have these observations that have some other underlying aspect to them. So they're not truly independent. Thirdly, we want to ensure we have approximately normal residuals. Generally, the residuals must be approximately normal. When this condition is found to be unreasonable, it is usually because the outliers or concerns about influential points. When we want approximately normal residuals, what this really means is when we look at the residual histogram, we want to make sure that that shows something that is approximately normal. It doesn't need to be perfect, but approximately normal to fit what we want to use with hypothesis testing. Remember, we always want to use normal distributions. Lastly, we have constant variability. This means that the variability of points around the least squares regression line remains roughly constant. To look at this, we are again going to look at the residual plot most commonly to see if there is any visual pattern. We want to make sure that it is constant in its shape, so there is no change in terms of the data spreading further away from the line in the residual plot at any given point. So we want to make sure that the points that spread away from the line is roughly consistent. When considering inference for a regression, we usually rely on statistical software to identify point estimates and standard errors for parameters of a regression line. After verifying conditions hold for fitting a line, we can use the methods learned in 4.2 for the t-distribution to create confidence intervals for regression parameters or to evaluate hypothesis tests. We have focused on the slope parameter since that characterizes the relationship between the explanatory and the response variables by giving the average change in y when x increases by 1 unit, the definition of the slope. If the data values extend to 0, it is also possible to investigate statistically whether the y-intercept is significantly different from 0. Couple other points before we see some examples of analyzing these using hypothesis testing. First, don't carelessly use the p-value from the regression output. What this means is the fact that the last column in the regression output often lists the p-values for one particular hypothesis, specifically a two-sided test where the null value is 0. Rejecting a null value of 0 using regression output allows us to conclude that the two quantitative variables are significantly correlated. If a hypothesis test should be one-sided or a comparison is being made to a value other than 0, we want to be cautious about using the software output to obtain the p-value. Overall, this means that when we're setting up our hypotheses here, what we're really going to analyze is the slope variable, which is often represented with a beta sub 1. This represents our slope, and for the null hypothesis, it is most commonly that beta sub 1 equals 0, which indicates that there is no significant change of one variable as another one changes. However, the alternative hypothesis says that beta sub 1 does not equal 0, which means that as one changes, the other one does change in turn. There is some connection there. That is what we're trying to show. However, Be careful of those assumptions we talked about earlier. Always check those assumptions. If conditions for fitting the regression line do not hold, the 4 conditions listed previously, then the methods presented here cannot be applied. The standard error or distribution assumption of the point estimate assumed to be normal when applying the t-test statistic may not be valid. Let's look at a couple examples of analyzing hypothesis testing. For this first example, we have a scatter plot, a histogram of the residuals, and a residual plot displaying the relationship between the percent of families that own their own home and the percent of a population living in urban areas for the 50 US states and Puerto Rico. We want to see if it is appropriate to fit a least squares regression line. In order to check if it's going to be appropriate, we want to look at our 4 conditions. The first condition of linearity, we want to make sure that there is a linear trend. And when we look at either the scatter plot on the far left, or we look at the residual plot on the far right, we don't see anything that would indicate otherwise. We do not see any other pattern here, maybe a curved parabolic shape or anything. So we can safely say for linearity that there is no nonlinear trend in the residual plot, so this seems to be fine. For the second point, it'll be very similar. For independent observations, we don't have any information from the paragraph that says this comes from a time series, and I would highly doubt it based on the context of it. So we can safely say that these are independent observations. For the third point, for approximately normal residuals, we have the histogram in the center here, and although this does not look perfectly normal, it does have a approximately normal shape with a peak here in the center and an approximately normal shape spreading from that, although it is not perfect. This one I'd say is maybe a little bit skewed, but not heavily, so we're probably safe here. However, the fourth and final point is really the one that's going to hurt us. The one concerning constant variability. If we look at the residual plot on the far right here, we see that points on the left of the plot seem to vary ever so slightly from the baseline. However, when we look at points further to the right, these points seem to vary far more than before. Therefore, we do not see a constant variability in the points here, which is going to be a problem. The variability in the residuals in the far right is not constant, as the variability seems to increase with larger values of x. Because of this, it is likely not appropriate to fit an LSR line. Now let's look at one more example. As shown in example 6.2 in the text, it is appropriate to analyze the relationship between family income and gift aid received by students at Elmhurst College. We want to use computer output to determine whether there is a significant linear relationship between the two values using alpha 0.05. Now, it already said that we analyzed this in the text. However, all 4 of the previous conditions do seem to hold. It doesn't have any nonlinear trend. We don't know anything about a time series. The residuals seem to be normal based on the graph on the far right. And the variability in the middle graph seems to be relatively constant. So, when looking at these graphs, we can say that there are no issues present with the 4 conditions. And therefore, we can move on and create the hypotheses for this. Remember that when we're considering our hypotheses for regression, what we're really analyzing is the slope variable, beta sub 1. And we want to say for our null hypothesis that beta sub 1 equals 0. That shows that there is no connection between the two. There is no relation. For the alternative hypothesis, we want to say that beta sub 1 does not equal 0. That, as in this case family income changes by 1 unit, then the gift aid from Elmhurst College will also change in turn. So for our hypotheses, we will set these up as the null hypothesis is beta sub 1 equals 0, and the alternative is that beta sub 1 does not equal 0. To compare this, we want to consider the fact that we're working with alpha equals 0.05. We want to compare that to a p-value. However, we see two p-values in the above table. We have one for intercept and one for family income. Reminder that the slope variable we are working with is the slope variable for family income. It's not the y-intercept variable. So we want the p-value for family income. 0.000003, which is incredibly small. If we compare that to alpha, we can say the p-value of approximately 0.000003 is less than 0.05. Because of that, we would say, as usual for hypothesis testing, that we reject the null hypothesis. Our final conclusion is that because the p-value is less than alpha, we can safely reject the null hypothesis and say that the data provides sufficient evidence that there is a significant linear relationship between family income and gift aid from Elmhurst College. If you have any further questions, be sure to review the example videos or ask your instructor.